thing in here right afterwards. So let's start out with this one, right? This is the first problem, right? We got a projectile coming in. By the way, same rooms as last time, right? Which is so it's even, 2 for one side and 2 for the other. That's fair, I think, right? The last exam we're all in the same room. We're over in, I think Gaines is where it's going to be for the final, huh?
Which rooms? Did you get a better average at? Which time's the first?
Oh, that's
the
a
first
question.
one to the last one?
I don't know. I did look that close, Mark, right? I should look into that. But the last one, we're all together over in Gaines. I got a big, huge room in Gaines for the final. So 8 a.m. Friday, work energy and impulse momentum, right? So this is an impulse momentum. We've got a projectile coming in and it's slamming into this thing and it's sticking to it. And then after that, it's kind of swinging up. And so this is a multiple part problem. We're trying to figure out how fast that bullet was going right before the collision, okay? And so again, I like to do these things chronologically. I like to think of the thing coming in, and then I have the impact first, and then we're gonna be short some information, and we have to figure out some other stuff. Also keep in mind, this was again from 2020 when we had a little bit more time. We had an hour to do the problems. This is during COVID. And so all these practice problems are probably, if you could do these, you should be able to do the other ones, because this is kind of the harder end of them. Because you might have noticed there's a little bit more going on with this one. We have to go a little bit tighter for our test, because we're gonna have 25 minutes to work on this. Okay, so let's do this, right? One of the first things I'm gonna do though, I'm gonna do some mass props. Mass props. Oh, not props. I'm gonna do some mass props. So figure out what the mass properties of this thing. And in particular, I need to know what the I is, right? So even right now, I could start talking about, well, where's my angular momentum? We're gonna use conservation of angular momentum. Where's that gonna be conserved about? I would say that it's gonna be conserved about this point up here. There's no moments around that point up there. Yeah, there's a spring there, but it's not gonna be engaged until after the thing actually starts swinging up. But like instantaneously when that bullet strikes it, there's no moment there. So I need to know what the moment of inertia of this object is about point O, right? I need to know that. And so that's what I have to do with my mass properties first. Also, this, right, there's this big rod, and then welded to the end of it is a big old disc on the end, right? So it's just one big object that kind of swings together. So I can figure out the moment of inertia of the whole thing, which is different than when we do this next problem here. We have this rod and then we have this disc. This disc is not, they're attached at point B, but they are not welded together, so they don't rotate together. This one's gonna rotate separate than how this one's gonna rotate. So in that one, we don't do a combined moment of inertia, but this one up here, we do a combined moment of inertia because the two swing together, right? And that's the easiest way to do this is let's just figure out the mass properties, figure out what the mass center is of this whole object, and let's just treat it as just one big object as opposed to having multiple objects floating around. You could do it with multiple objects floating around, but it's easier just to kind of combine it into one, okay? So mass props, I need to figure out what I is about O, right? The total I for this and this added together. And then I also have to figure out what the new mass center, it just makes it a little bit easier where the new mass center is with both of these things in, okay? So let's do that. So there's some things that were given to us. The mass, I'm gonna call that R for the rod. That was given to be as being 10 kilograms. And then mass of the disc, MD, that was given to us as being 20 kilograms. I'm kind of stating some things here. And then I need to find, like I said, I'm gonna do I about O, right? I about O, I want the total I about that fixed point, okay? And I'm gonna do it, I'm gonna figure out I about O from the rod, right? Because again, you're gonna have to use the parallel axis theorem to get the I about O right here, because I've got this object and this object. I know what the moment of inertia of a rod is about its end. That's just 1/3 ml squared, right? So I can do that. And then I have to figure out what this moment of inertia is about its own mass center, and then use the parallel axis theorem to get about O, okay? So I/O about R, that's just gonna be mr times L squared divided by 3, right? And if you plug in our values on this one, this ends up being 83.33 kilograms meters squared, right? So that's just I of the rod about O, okay? I now have to figure out what I about O from the disk is, right? And so, yeah, you would need to know what the moment of inertia of the disk about its own mass center is. That is 1/2 moment mass of the disk times r squared. That's about its own mass center. And then I add on to it its mass times d squared. Right, so that's the parallax term. So that will give me I of the disk about 0.0, right? And some key things here, this radius here, that radius is 2.5. That was 2.5. This distance d would be 5. All right, MD, or I said what that was. So this ends up being equal to 562.5. And that's kilograms meters squared. All right, so that is, now I've got both of them about O, and then I just add the two together. It gives me the total I about O. It'll just be IOR plus IOD, which ends up being equal to 645.83 kilograms meters squared. All right, just some mass props that I have to get there. Not all of them yet, though. Any questions about that, what I did there? Right? And this is, it's pretty quick. We got to do this one on the fly, figuring out what that moment of inertia is. Right? You could make the table if you want. You have time to make the table, probably not. So just understanding how this works. Once you get them each about 0.0, once they're both about a 0.0, you just add them together. It gives you the total moment of inertia. Right? And the reason I picked 0.0 is because I know the angular momentum is conserved about that. It's also a fixed point. It makes it a lot easier if I do that. So I've pre-calculated that. So when that comes up later, I've taken care of that. Okay. The other thing I need to know, you don't have to. You could treat these things as being separate, but it is a little bit easier when you figure out the new mass center. And we'll call that new mass center Y bar. Y bar, and that's just going to be a weighted average. So I'm going to have the bar is 10 kilograms. The distance to its mass center is 2.5. So 2.5 times 10, that's the bar. Plus the disk, its distance to its mass center is 5, and its weight, or its mass, is 20. Right, and we divide by the total mass, which is 30 now. And so that ends up being equal to 4.16 meters. The benefit of doing that is when we do the energy stuff a little bit later, right? When we do energy, I just have to track the location of the new mass center, and there'll just be that one term, right, for the mass center changing. Or if I didn't do the new mass center, then it would still work. When I look at the potential energy of this thing, I'd have two terms. I'd have the mass center of this and the mass center of this, and you'd have to keep track of both of those. So it makes it a little bit easier just to get one combined mass center. Right, so that just tells us that we have a mass center right here-ish, right? And that distance there, 4.16 meters. That's what that mass center is. Any questions about the mass props? Right? Again, do you have to do it at the beginning? No, you could do it on the fly. You could be going down and you could be filling stuff out and then have to calculate these moments of inertia. That's fine. But by the way, this is so nice when you do it, when you organize it this way. Like when I'm grading it, right? I just look at it and be like, oh, look, he calculated the mass properties here. Even if you made a mistake, at least I could see where you made the mistake instead of just pure randomness, what it feels like sometimes when you're writing. And I get it. You panic a little bit and you start filling in shit all over the place. I get it, but try to keep it tight. Try to keep it tight. Again, look how shitty my handwriting is, but it's still tight, right? It's still tight, right? It's easy to follow. Okay. All right, mass props, right? So then again, like I said, I like to do these things chronologically, right? So I'm gonna do angular momentum first and then work energy afterwards. Both though, it's nice just to, again, the free body diagrams aren't as important in these problems, but sometimes it's nice to do just to kind of make sure we know what's happening and see where we could deal with this. So I'll just do a quick little free body diagram. Right, I got my new mass center here. Force is acting on this thing. I've got mass times gravity going down. Right? It's the total mass. It's acting in the center of that. I've got the bullet going to strike, or the bars, or the disc striking the bullet, and the bullet striking the disc. So both of those guys kind of canceling each other out. Right? And then I got the reaction. Right? I got OX and OY. And we've got this moment eventually from the spring, right? But it's not active at first. You know, and some of these problems are weird. Like I said, the last problem in your homework, we had that like disc, that rod that was falling and it struck the thing and then it swung back up the other direction. That was weird. I mean, like I had to even make a video to try to explain to you like what the hell was happening there, right? Because technically there is a reaction there, which would mean the linear momentum is not conserved vertically, but then we just say, well, it just acts really quick and then it goes away. And this is the same idea. That moment from the spring when that bullet strikes it, it hasn't really reacted yet. It has to move for it to react. And so it really isn't there until, because we're trying to look to see is there a place where there's no moment, right? And we're going to say that there's no moment right here because these guys are acting through the center. This is lined up with that, so it doesn't cause a moment. These guys cancel each other out. So I'm going to say angular momentum is conserved about that. Right? The other thing I'm going to use this for is to say, is there any external forces doing work on this? There's not, right? There's no external force. There is no external moment, right? There is a spring, but we're going to put that in potential energy term. There is the OX and OY, they won't do work. It's just like the normal force. They don't ever act over any distances. They just act there and prevent movement, so those don't do any work. The bullet stuff doesn't really do anything, right? And mass times gravity does work, but we're going to put that in the potential energy term, so there's nothing there, right? So there's no external work on this guy right here. So that's my free body diagram. You guys could speak up. See, if it doesn't make sense, it's okay. Tell me. It doesn't make sense.
Does the spring not do work on the system?
It does do work. It absolutely does work, but we're going to put it in potential energy, right? You could count it either place. You can put it in as doing work, or you can put it in as potential energy, but you can't do both, right? I mean, you could, but you could do like half on one. Don't do it, okay? Just do it either. We're just going to say that it is in our potential energy term. We're not going to count it as doing work, okay? One or the other. Treat it as one or the other. I think it's easier. I like to think of it as potential energy, right? There's nothing when it's not stretched. When it gets stretched or twisted or whatever, in this case twisted, then it stores energy, right? As it goes. Okay. All right, good. Thank you for the question. All right, we're gonna do angular momentum. We're gonna go 1 to 2. This is gonna be angular momentum. Take 1 to 2. All right, it's gonna be angular momentum. Again, I like to do it chronologically. Right, and I guess I should label these up here maybe. You got 1 coming in, we got 2 right after the collision, and then we have 3 when it swings up. Wherever it swings up to. So 1, 2, and 3. So 1 to 2 is gonna be conservation of angular momentum. Right? And so what that tells us, we found a spot where the moments are equal to 0, which means that my angular momentum before the collision, HO1, is going to be equal to the angular momentum after the collision, HO2. Right? Again, H stands for angular momentum. Again, weird, right? Before the collision, it's just the bullet moving, right? So that's the only thing that we have moving before. So it's that particle. What that is just R cross MV. R A is seen from O, crossed with mass of the bullet times the velocity. I guess I'd probably call it A. I'm going to call it massive A instead of mass of the bullet. We'll call mass of A times the velocity. Right? That's the angular momentum before the collision, right? The bar and the disc attached to it, they're not moving yet, right? So they don't have any angular momentum. It's just that, right? And that's going to be equal to the angular momentum afterwards, right? But what's interesting about this, right, is that in the problem statement, it says you can neglect its mass after impact, right? So it's 0.1 kilograms. It's traveling really fast right before the collision. We don't know how fast it's going, but that's what we're after. And then once it collides, Remember we did that example and showed that really once that little teeny mass gets attached to this big mass and they start swinging together, it doesn't really do anything. And so we're gonna let this thing neglect the mass afterwards. And if that's the case, please take advantage of it. It makes your life a lot easier. It just makes it, you don't have to track the location of the bullet if you're doing that and see how much it's swinging. You just get to ignore it. In this case, it makes it really easy because the angular momentum right after the collision, the only thing that we're gonna have, since there is a fixed point, is just gonna be IO times omega. That's it, right? Because it's a fixed point. If it wasn't a fixed point, we're doing it about a mass center, there'd be IG times omega, right? And then if it was a moving point, there'd be an extra term in there. But this is it, that's it right now, right? You have the angular momentum of that bullet coming in, of that particle, and then all of it just goes into this, right? And especially since I made a combined I, there's only one I, right? Because I combined it. Could I have left them as separate? I could have, right? And it would have been, there'd be some IGs and some weird shit going on. But by doing the combined here, it makes it a lot easier, okay? That's it, right? I can't do this yet because I'm after that velocity. I need to know what omega is first, right? Because you got to work this problem backwards. They told us how much it swung up, and so I got to go over to work energy to figure that out and come back to this omega. And once I get that omega, I can go back to this velocity. Yes, sir.
We don't have the bullet in there because mass index.
This is the bullet. Is the bullet?
No, I mean on the right side of the equation.
Yeah, that's right. Because I get to ignore it. Right, because I said you can ignore it, but technically, you're right. You'd have this. This would be VA1, and then I would have plus RA is seen from O, crossed with MA times VA2, right? But because I said that I get to ignore that, right, makes my life a lot easier. Great question. I'm gonna put red through it.
Could you solve it if you?
Yes. I mean, I can. Could you? No. But no. Yeah. You absolutely could, right? But then what you would have to do is you would just have to do a little bit more kinematics, and I would have to relate omega to that velocity, which I could, right? And we did it in an example in our class, right? You would just have to take a step, from the fixed point down to where the bullet's at, right? And then I would have to use this omega. I mean, it'd be R cross. It would be omega crossed with RA is seen from O is what it would be, right? And it'd be R omega is what it would be. But you would just have to do a little extra. But what's nice is we don't have to do that. Look back at the notes, we do it. But then I said, and in the notes I said, hey, look how small this number is. Let's just forget about it. We'll make our lives easier, okay? And then remember that. Wink, okay? Don't ignore it, okay? I even put it in bold and italicized. I've actually made the test and I put it in there, and there's a part just like this where I say you could ignore the bullet afterwards, and I put it in bold. So please ignore it. It makes your life a lot easier, okay? It makes your life a lot easier. Wink, wink. Okay. So again, I can't do this yet, right? I need to know. Oh, well, let's put in the numbers at least. Let's get primed from when we do get the values. RA is seen from O. Right? RA is seen from O. I'm going this direction, right? And that distance is -5 in the J, right? So this is -5 in the J direction, and I'm going to cross that with MA, mass of A, which is 0.1 kilograms. That's the mass of the bullet, times, negative VA in the I direction, right? Because this bullet's coming this way, which is in the negative I direction, right? And its magnitude is VA, right? And that's going to be equal to IO times omega in the K direction. Okay, so then I'm stuck right here, right? I need omega. Need omega. Go to work energy for this, right? Because they tell us how much it swings up. Okay, so now we go 2 to 3. All right, state 2. Oh yeah, I'm gonna put an arrow over that. 2, 3, oh yeah, look at that, 3. Right, that's gonna be work energy. Right, in that case, again, when I do work energies, we already look to see what's doing it. I do this, I go, I just say it just like that. T2 plus V2 plus work done from 2 to 3 is equal to T3 plus B3. Right? Work energy equation. Right? And I'm going stage 2 or state 2 to state 3. Right? Come in, right? What is the energy at state 2? That's what I'm after. Right? I want to know how fast it's going at the beginning of this state. So it's in T2, so I can't cross that out. Potential energy at state 2, right after the collision, right, depends on where I set my datum, right? I'm gonna set my datum, I like to put my datum at the bottom being equal to 0. So in this case, I'm gonna set this y equal to 0, right at that point, right? And it's gonna swing up from there. So I'm gonna set it up so that I have no potential energy at the beginning, right? Because that spring isn't twisted yet either. It's in an unstretched position, so there's no potential energy from the spring, and it's low height. It hasn't swung up yet, that's what it is. Again, there's no work being done from state 2 to state 3, right? And then the thing is swinging up until it stops, which means at state 3, there's gonna be no kinetic energy. It's not gonna be moving anymore. And so I'm basically going from kinetic energy at state 2 to potential energy at state 3. That it stops moving, and that's why the potential energy, or that's why the kinetic energy, it basically takes all of the kinetic energy and transfers it into potential energy, right? And so that's it, right? So now I just expand on this sucker, right? T2, it's great, it's a fixed point. It's just gonna be 1/2 IO omega squared. That's the kinetic energy right after the collision, right? Because I combined the two together, and there's a fixed point. That's the only term I have. I don't have to track where the mass center is. I don't have to track the mass center of the two objects. I've combined them into one, so that's it. That's the kinetic energy at state 2, and that's equal to 1/2 times k theta squared. That's the potential energy in the spring, plus mgh, which is the potential energy from change in height. Right? That's what I'm saying right there. So I didn't use it as work, but I put it in as potential energy. Yeah.
Could you show how you would do it as work as well? Or is it just like
No, I think I got it. I think it goes over here. You say, but I don't want people to do it that way. Okay, but I'll say, don't do it this way. I'll put it in red. IO omega squared, and then we'd put in minus 1/2 or k times theta 2 minus theta 1 squared, maybe, or is it squared? It's squared.
You sure?
No. Yeah, not at all. And then one of them is 0. This one, and just to show you that it ends up being the same, one of these is 0, right? Theta 2 is 0. I don't know exactly, but one of these is 0, right? And then you could see that it's minus 1/2 k theta squared on the left-hand side, but if I just put it on the right-hand side, it's a positive value. It's the same, ends up being the same thing. I did something wrong in there, I did. If it's theta 3 minus theta 1 squared, I don't know, but one of them's 0. And then the signs are off. I just wanted to show, this would be the same. Oh, did I say minus there? I meant plus right here. And then I fixed it. And so then see how this would be 1/2 k times theta, oh, that's not theta 1, that should be theta 3. 3. It's something like that, and you can see that, look, that's 1/2 k theta squared. Negative on the left-hand side would be the same as positive on the right-hand side. So you get the same answer, it's just you put it on the left-hand side versus on the right-hand side, okay? And so but again, I don't like it this way. It's so much easier to me in my simple brain to handle it as just, I can only treat it as one thing. I think about potential energy. Cool? Good enough?
Yeah.
Okay, good enough. Good, thanks. Whew. It's something like, I think that's kind of it. That's the right, this is what the solution should be, what I just wrote there. because when it's on the right-hand side, it should be the same thing, and then which would be the case the way I have it written right now. Something's off though. I did some fudging in there as well. Okay, so now, right now I got it down. This is the equation I need to solve. Right, that's the equation I have to solve. But I'm after omega, so I need to do a little bit of kinematics to figure out what theta is. Right, how much it's twisted. Actually, it's given to us. And then I need to figure out what MGH is. And once I do that, then I can solve for omega. So then at this point, we go to kinematics, right? Just a little bit of geometry, right? I do a little bit of kinematics to figure that out, okay? They give this to us. They tell us what theta is actually right off the bat. Theta ends up being equal to pi over 3. They gave us that in the problem statement. They say that it swings up for a theta equal pi over 3. So that's given to us, right? You got to do a little geometry here. And so this is to figure out the height. This is 4.16, right? This is down to the mass center. And then it swings up, right? And then this ends up being, since it's swinging, this is still just 4.16. And then this distance there, that's theta, that's pi over 3, right? And so what you're looking at is this triangle here, right? The hypotenuse, right, is 4.16. And so when it swings up, it's still, it was down here, right? It was down here, but then it swung up to here. Right, it swung up to here, right? So that's still 4.16, and so then the height difference is this distance right here, right? That's what I want to know, is how far that height changed right there, right? And so then this would be 4.16 minus 4.16 times cosine of pi over 3 is what that change in height would be. And then that ends up being equal to, if you calc it out, 2.08. Right, so that is what my change in height is. That goes, that height right there, right? Let me expand this out, right? Because now I've got all the terms. Let me expand it out. This would be 1/2 times my I, which is 645.83 times omega squared. That's what I'm after. Is equal to 1/2. My K is 1,000. My theta, again, is pi over 3. That's squared. Plus my total mass, the two together, right? Because we've lumped them together, is 30 times 9.81. And then the height is 2.08. And so then my omega, that's the only unknown in there, is plus or minus 1.9 rads per second. Okay? That was one of the questions we were asked for, right? What was omega? Right after the collision. So that's the omega at that state, right? And then to figure out what the initial velocity was, I take that and I just put it up right there, right into that omega. Right, and again, just to make it, this IO is 645.83. Right. And so if you calc that out, you get VA. You just solve for VA in that. The velocity of A ends up being equal to what we said, what was given up above, 2449 meters per second. I did that. I mean, while it is a little bit more difficult, it still is doable, right? In 25 minutes. We just did it in 30 minutes, but we had some questions along the way. Yes, sir.
How come the angular velocity is plus or minus?
Because when you solve this, there's an omega squared, so it comes out plus or minus. Right? You lose the sign. So when you solve this, plus or minus, and then you just got to use a little bit of, logic to figure out which way it'd be going. right? It'd be negative, right? So it's going to hit and swing this way, right? So our finger, so we know it's going to be the negative 1.9. Yep, you got to apply a little logic to it. Yes, sir.
So with the height difference, this is where I'm thinking our mass center didn't really matter, because I could have used a different coefficient. I could use 5 minus 5 cosine, and I would have got the same.
You'd have had two different ones though. If you don't combine them into one, I would have one for the mass center of the rod, and I'd have another one for the mass center of the disc. And so this MGH, instead of just being one term, there'd be 2 terms.
Yeah, but I could cheat.
Yeah, or you can just do this, right? Or you just do it this way, right? This is a clean way of doing it. That's no cheating. We're not going to cheat. Yeah, but yeah, I mean, there's other ways to do it, but try to do it in a nice, logical way. But look at this, right? Look, I get one of these things, and I go to grade this one. I'm happy. I'm excited. I'm like, look at these people. Even if you got the wrong answer, I'm just be like, close enough, man. Good job, right? But when I get the ones that are just like, you know, I grade 100 of these, right? And I get the ones with shit all over the place, and what's that?
I can't write that small paper.
No, you're right, but sometimes, I swear to God, I swear some of you guys are writing like this. I think you got a crayon and you're just fucking going to town like this. I swear to God, right? Get a straight edge. For reals, right? You're engineers now. Just carry around a straight edge, keep it in your pocket protector, right? You pull it out, right? Get ready for it. Yeah. I swear. Right, you got crayons, you pull out your crayons, grab it with your hand like this. just like this, right? You think it's funny, but you guys do it, right? And then, right, not only that, and then you have like a page of algebra that leads to the wrong answer, right? It drives me bonkers. It's so tight. Okay, let's do this guy. We're getting kicked out in 30 minutes, so we got to do this one. All right, again. I like this one. I've given this one several times in past, right? In different varieties. So this guy is sitting up here. It's a little bit different because they're not attached, right? AB is not attached to the disc, right? It's allowed to roll. And so this thing's gonna whip down, and as this thing whips down, right, this guy's gonna rotate. This is rotating. Right, this disc is rotating, and then this bar is rotating, and then this disc is going to be rolling around, right? Because it's a rolling wheel. It's touching right here, and it's moving without slip, and so it's gonna go roll down while this thing's rotating down. Okay, and so this is a work energy. There's no impact associated with it. I just tell you, this has got a radius of 1 meter out to here. This has a radius of 2 meters out to here. They tell us its mass is. It's rolling without sleep. It's rolling without slip, right? And I put, just to make things a little bit more interesting, I put a little spring in the middle of this thing as well, okay? So this one, straight work energy. I'm gonna skip the free body diagram. Look at the free body diagram, right? There's no external forces doing work. And what you're looking for external forces is, we're getting good at it. We should probably know, there is no big moment applied right here. There is no big force applied. There's nothing like drawn as being external, which means that there is no external work, external forces doing work. And again, this guy, really the spring will do work, but we're not putting it, we're gonna put it in potential energy, right? And then gravity really will do work, but we're not gonna do that. We're gonna treat it as potential energy, okay? And so this one, you wouldn't come up with a mass center, and you wouldn't come up with I, right? We're just gonna leave those things as separate. You could probably do a combined mass center. You could do a combined mass center if you wanted to, and then that would just give you one less term, but this time I'm gonna keep them as separate mass centers. But you couldn't do one combined I, because this guy's rotating as this guy's coming down. They're not attached to each other. They're not kind of swinging together, so you wouldn't have a combined I. Okay, so then let's do it, right? Skipping the free body diagram, going right to work energy. Right? Oh, but I'm going to do a little bit of mass props. Right? Again, you don't have to do it at the top, but I like to do it just when I'm on a roll. I don't have to stop. Mass props. I don't have to stop and do it. The only thing I need with this, though, is what the moments of inertia are, right? This is nice because I got a fixed point. Whenever I have a fixed point, it's nice because it just gives us one less term and one less thing to track. I got a fixed point A, so I'm going to figure out this. I could do the I of this bar about A because that's a fixed point, but I can't do anything of this about A because it's not attached to that fixed point. So I could just do IAB. So I'm going to do IAB about the fixed point, which is just IAB about A. This is going to be 1/3 ml squared, which is equal to 1/3. The mass is 5. The length of it is 2 squared, and so this ends up being 6.66. Right, and this is kilograms meters squared. Right, and then I of the disk, I need to do its mass center here. A disk about its mass center, right? This is something I would give to you, right, up at the top or something. 1/2 mr squared is a disk about its mass center. So 1/2. The mass of that disk is 10. Its radius is 1. So this ends up being 5. Okay. And again, I'm not going to do a combined mass. I'm going to treat these things separate. There's my mass prop. Okay. Again, just to get them up here so that I don't need to worry about them later. All right. Mass props. All right. Now I'm just coming in. I'm ready for the energy equation. Right. Jump right in. We skipping the free body diagram really, but I'd put it, just free body diagram if you want. Not as important in these problems. You're just looking for external forces doing work. Okay. Energy equation, T1. T1 plus V1 plus work being done, 1 to 2, equal to T2 plus V2. Okay? Come back and say, hey, what do you got going on? Right? Thing is starting at rest. Starting at rest, no kinetic energy. It's not moving. Right? Potential energy at the beginning, yes, because I'm gonna define being at the bottom as being at the bottom. It's not having potential energy. I like to do it that way. Okay. Work being done from 1 to 2. Like I said, there's no external forces doing work. Right. Kinetic energy down at the bottom. Yes, that's where I'm. That's what I'm after, right? I'm after, by the way, what we're after is omega of the disk and omega of AB down at the bottom. So we're after those velocities. So we're after the kinetic energy that's happening down. It's after down at the bottom. Okay? So I'm after that. And then potential energy down at the bottom. Where the height, I'm going to set that being equal to 0, the MGH being 0 down at the bottom, right? I'm going to have that being 0, but there is going to be the spring. The spring is going to be wound up down at the bottom. So I can't cross out V2. So that's everything I can cross out. So now I expand on this thing. Right, 3, expand. Right, expand this sucker out. Ooh, there's a lot going on in this. Right, I got mass of AB times G times HAB1 plus mass of the disk times G times HD1. Right, so that's all I have on the left-hand side, right? Mass times gravity times height times the 2. Do different heights at the beginning. Right, that's a D. D1. All right, that's good enough. Mass D. Let me make that more clear that that's a D. Okay. Okay. Now, the right-hand side, there's all sorts of stuff going on, right? The potential energy on the right-hand side is 1/2 IAB times omega squared. For AB, for this rod AB, since I'm doing it about the fixed point, that's the only term I have. Boy, that drifted on me. I think I can follow those lines. Okay, the only term I have is going to be this, right? It's only going to be this term. I don't have to do the 1/2 MV squared part because I'm doing it about the fixed point, and I did IAB about the fixed point. So that's the only term I have for that rod, okay? So that's just the rod. Now I got to do the disk potential energy. So the disk potential energy, I'm going to have plus 1/2 mass of the disk times V, their point label, yeah, B, VB, 2 squared, plus 1/2 I of the disk times omega of the disk squared. So that's the potential energy of the disk, right? I have to track, there's two terms on this one because there's energy associated with the mass center translating, right? That's this term. No, that's this term. That's the 1/2 mv squared is the mass center translating of that disk. And then this term right here is the kinetic energy of that disk turning. And you have to do both of them because there isn't a fixed point. So I have to track both of those things as I go down. Whereas this guy, I only had to do one because I used I about A. And by doing that, it kind of accounts for both of these. If I did I of this rod about its mass center, then I would have I about the mass center times omega squared plus a 1/2 mv squared of the disk as well. You'd have two components to that as well if you did the mass center. What's nice about doing the fixed point, you only have to do one of them. Okay, so that's all the kinetic energy. Yes, sir.
What's your potential term? You said you had a...
Sorry, potential. By potential, I meant kinetic.
Okay.
Yeah.
Is this all kinetic right
Yeah,
now?
we're not done. Yeah, this is all kinetic. This
Okay.
whole thing here is kinetic,
Okay.
right? This is kinetic energy associated with the bar rotating. This is kinetic energy associated with the disk translating and the disk rotating.
Why does the bar not have a velocity? It just has a
Because I used the moment of inertia about that fixed point.
Okay.
When you do that, when you do it about the fixed point, then you only need this term.
Okay.
That's a benefit. That's what's nice about it. If I would have done it about the I about the mass center, then I would have this term and this term for that rod.
But because the disk is rotating and it's moving, it has two
Yes,
terms?
correct. And there's no fixed point that I can go off of.
Okay.
Yep. Okay, so that's all the kinetic energy that's in there. Now I got to do the potential energy down at the bottom, right? Which is going to be 1/2 K theta squared. Right. Okay. So that's the potential energy that's in the torsional spring at that point. Okay, so we're doing, that's all of it. Okay, the problem is, look at all these freaking unknowns, right? Different heights, HAB1, HD1, omega, VB2, omega D, and theta. All that stuff have to be related to each other. You got to get down to one unknown. I got to do lots of kinematics here. So kinematics. You okay, Mark? You panicking? You panicking right now? Right? 4. But they all follow these same steps. It's always the same steps, Mark. It's always the same steps.
Falling, whatever.
Kinematics. Okay? And again, the kinematics I want, right? It's going from this state up here down to this state down here, right? And it's kind of nice to look at this. It's going from there, and it's going down to here. And for some reason, it got smaller as it went down. But note that, like, the kinematics, a lot of the kinematics I have to do are over here in state 2, right? So that you think about your kinematics being in this position that we have right here, okay? Being in that position, right? So then I gotta somehow relate all these things together. And this is where you just go back and you're like, okay, how did we do kinematics before? Right? Well, I could go from A, that's a fixed point, and I'm gonna go down to this point right here in the middle. That's the velocity of point B, right? Right? I'm gonna go that. And then I could go, the other point I know something about is I know right here's the velocity is equal to 0, and I could go up to here as well, right? Or I can go from here to here. I can go here to here, and then here down to here. And it should give me a relationship between how this one's moving relative to how this one's moving, right? The other thing, you kind of look at it and probably figure it out, right? We should get a relationship, but I try not to have you do this. I want you to do it the way where you step through it. But right, if I have this rod that has a radius of 2 meters, and if it rotates down 2 meters, how many times is the thing that has 1 meter radius going to rotate around?
7.
It's gonna go twice as much, right? 7, as I said. It's gonna go twice as much, right? This thing's going down, right? And if this thing moves, the other one's got to rotate twice as fast because it has half the diameter, right, or half the radius, right? So that would come. We should get some relationship that just says that whatever the bar rotates, the disc has to rotate twice as much, right? We should get a relationship, or 7, or 7. Yeah. So let's come over this. Do that. So I'm gonna go right. I'm gonna go to the velocity of B. I'm going to say the velocity of B, and I'm going to go from A. So the velocity of B is equal to the velocity of A plus omega AB crossed with RB as seen from A, right? Just my kinematics equation. VA is 0, right? Omega AB is in the K. Just always assume it's in the K. Omega AB in the K direction. I'm going to cross that with RB as seen from A, which is -2 in the J direction. And what I get there is 2 omega AB in the I direction. Right? So that's what my velocity B is coming from A. Right? And I usually, sometimes I like to go, let's just go to B from a new point. What do I say? VC. We'll call this C down here. Right down at the bottom there. We'll call that C. So we're going to go, and we know that that velocity is 0 as well. Say velocity of B is equal to the velocity of C plus omega of the disk now, because we're on the disk, crossed with R B as seen from C. Right? BC is 0. Right? That's the point where it's touching, and a rolling wheel has 0 velocity where it touches. This is omega D in the K direction. I'm going to cross that with 1 in the J direction. That's that. I'm going from here, point C, up to the middle right here at B. So it's 1 in the J direction. And when I get here, this is equal to negative omega D in the I direction. Right? And they're both giving me the velocity of B, so I could set those two things equal to each other. Right? So I set VB equal to VB, B equal to VB, coming from both of those different directions. And what I get is 2 omega AB in the I is equal to negative omega D in the I. Right? Just like I said, we should get one going twice as much as the other one. Omega AB is equal to negative omega D over 2. Okay? There's one relationship that we have. Okay? I need to come up with what relationship. I need to get them all down to one thing. So that's what I said. That, if you look at it now, that should make sense to you, right? Right? This guy rotates down. This guy's going to have to keep up with it, but it has half the radius, so it's going to have to go twice as fast. It's going to rotate twice as much in the amount of time that AB rotates. Okay? We okay with that? We okay? Well, Mark, you okay? Barely. Okay. Heights. You figure out heights, right? It went from up here. I got two different objects, right? It went from up here, right? And it's going down. This is going to be the middle of this guy. YAB1 equal to 0, right? And this one down here would be YD1 is equal to 0, right? And so up here at the top, right, because we're talking about potential energy being up at the top, this is going to be YAB2 would be equal to 1, right? And then also up here at the top, you can have a separate datum. You can treat them as being separate datums. This is YD1. That's going to be equal to 2. Right? You can have separate datums for each one of the things. Right? It's going YAB is going from there, and it's swinging down. And when it's down, its mass center just went from 1 to nothing, right? And then D though, it started out up here, and when it swings down, its center of mass goes all the way down to the bottom, which would be 2 meters. Everybody see that? You can set up two different datums because just a change is all that matters, right? So YAB goes from, its mass center goes from here to here, right? So that distance right there is just 1, right? And then D's mass center goes from here down to here, which would be 2, right? And so then that would be 2. So now I got those guys, right? Those down here. Have them all in one place. Y D1 is equal to 2, and Y AB1 is equal to 1. All right, and then the last thing I got to do is I got to figure out how much they rotate. There's a couple ways to do it, right? I need to know theta, right? I need to know theta is the last thing I have to do is figure out how many times this thing rotates around. And the reason I need that is because I need to know how much this spring gets rotated, or how much that spring gets twisted up. The easiest way to look at it, right, is come back to this that just says that the disk is going to rotate twice as fast as omega AB, right? And so if the disk is rotating twice as fast as AB, then it means that it's going to have twice the theta that AB does, right? And so how much AB rotates down, that's pi over 2, right? This angle right there is pi over 2. Pi over 2, right? And so that means that this thing would rotate around pi, right? There's a couple different ways you could do that. That's the easiest way to do it, right? Because of that, then we know that theta AB is equal to theta D over 2. Right? It just shows if the velocities are that, then the thetas have to be that. You could also work it out with like arc lengths. You could come in and say, all right, well, I know how much this thing rotates down, and then I could figure out how much that thing rotates about. But we just know, I mean, since one's going twice as fast as the other, then if that rotates down pi over 2, then theta of the disk is pi. It has to be twice what that is. That's the easiest way to think about it. Okay, so that's everything now. We got it all. So now we come back down to this. I'm gonna copy this and put it down below here. All right, last step is solve. Okay, I'm gonna paste this down here. Okay, that's what I wanted to copy it down so I can go from here. All right, that's the guy I'm going with. So now mass AB is 5. G is 9.81. The height there is 1. Plus mass of the disk is 10 times 9.81. HT1 is 2. Right? That's the left-hand side. The right-hand side. What is that? The bomb. 6.66 is that I negative omega D over 2 squared. I'm going to put everything in terms of omega D plus 1/2 times 10 times negative omega D. And these are things I found in my kinematics. Squared plus 1/2. It's my I, 5. Here's my actual omega D squared plus 1/2 times 10 times pi squared. Simple as that, Mark. Simple as that. Simple as that, man. And that's it. The only unknown in all that is omega D. This is
over 2 on the second one.
What's that?
Negative omega D over 2 on the second.
I know, I would set it up to inspire. That's what I got.
Okay, I wasn't listening. Okay, I'm listening now.
1/2 10 times omega D.
1/2 10 times omega D.
That's supposed to be over 2. Omega D over 2.
No, because it actually is. That's V. Which one? Is it 10? 1/2 10 times?
Yeah.
That is what VD is.
Why is it negative?
Because that's what we got up above in our kinematics. But it doesn't matter. It gets squared anyway. So, but up in our kinematics here, right here. VB. VB is equal to negative omega D.
Oh.
Right there.
Oh, okay.
Yep, so I substitute that down in below. So omega D would end up being equal plus or minus 4.85, but it'll be the negative. We know it's going to be rotating negative. And then omega AB, we can get with the relationship that we had up above, 2.42 rads per second, right? It'd be half of that, right? There she is. Okay? Yes, sir.
On the potential energy at the end, should that be pi over 2?
No.
Why is that pi?
Because yeah, great question, right? It goes back to this, that this rotates, that right there, right? That distance there that the bar rotates down is pi over 2, right? 90. But then this disk, I need to know how much that disk rotates around. And it's going to rotate around twice as fast, which means it's going to go twice as many times as what AB does. So instead of being pi over 2, it's going to be pi because it's going to go twice as much.
Because the spring's only attached to the
The spring is only attached to the disk, and it only cares about how much that disk gets wound up as it goes down. So I need to figure out how much the disk rotates around, and the disk rotates around half as much as the bar rotates around. So it'll be at pi. Yeah. You okay? Yes, Mark.
Just for people watching, the subscripts for the Ys, you have 2 YD1s.
Yep. This is 2. These are both 2. This is 2, and this is 2. I wasn't done yet, Mark.
Then you have a 1 or 2 on the.
And then this is 1. And then this is a 1. Look at you guys wanting accurate notes. Those are 1. Right? Because that's what it is. They start out 1 is up above, and then they go to 2 down below. So yeah, I messed that up. That was flying through. Cool? Extra credit, I'm not going to do it. It was a pain in the ass. I don't think anybody did it that year. I redid it again just to make sure I could do it. Here it is. It gets weird. It gets weird. Yeah, no, it wasn't a fair extra credit on this one, right? So it comes up, it starts out the same potential energy up at the top, right? So it start up there, so I use the same terms I had before, right? I use these same terms. This is still the potential energy right before it gets released, right? And then it comes down, and I'm going to have this 1/2 k theta squared, and then it's not moving when it swings up the other side. It's not moving, and so this is, it just goes into this, it's all into potential energy of the disk when it raises back up, and then there's some weird shit you have to do with I introduced a new angle that was going up, and I have to relate all HAB1 and HB2 and HB3, and then that's the equation, that's the answer, that's the real answer. Goes up 1.675 meters on the other side, but that was a little unfair. Too much geometry. Cool. Any other questions? Everybody's good? We're ready to go? Again, that's a little much. Those are a little much. Expect a little bit less, but if you can do this, you're good. You're good.
What homeworks and sections should we study for this?
Everything's the last one. I don't know what the last homework was. 11? Homework 11? Okay. Yeah, the last homework you did, it goes to that. Okay, yep. And the homework before that. Yep.